welcome to this talk. I hope I can give you some historical background of Ingula, where it sort of started and why we construct Ingula, and a couple of sort of design criteria if you ever want to design the pump storage, but that will be very short and brief. Right, why pump storage? If you look at the sort of load demand during a typical week, you would see that it varies in winter from about 24,000 megawatt to about 36 plus thousand megawatts. So it's quite a variance of about 12,000 on a typical winter's day. In summer that is less, so you can see the red line. Now, to follow that demand with coal-fired stations is not very effective. And coal-fired stations preferably want to follow more or less that brown line that I sketched in. A slight variance, say, between about 30 and 32 odd thousand megawatt spread over 13 coal-fired stations is hardly a huge difference of each power station. Now, in order to operate these coal-fired stations in such a mode, you will see that in the off-peak period, that is during the night, if you then generate more than is required, you actually have an excess energy. And here you have less than the demand. So what we do in pump storage, during that excess energy, we store that energy. If you ever heard people saying you can't store electricity, bull, we're doing it every day with pump storage. Basically, you take that excess energy, you pump water from one reservoir, that's our lower reservoir, to the top, and you store that energy in the form of potential head and volume of water. During the peak demands, we just release that water, let it flow through the turbines and generate electricity. Now that little peak here, that was actually always planned for our open cycle gas turbines. That's the one that we have in Cape. Although with this huge pressure on our system, we sometimes run these open cycle turbines almost at 50% of the time. At a huge cost because we run them on diesel and not on gas. We don't have enough gas, at least in South Africa. And so you follow the pattern during the typical weekly cycle. If you look at pump storage compared to other systems in our total mix, you'll see that pump storage becomes a viable option if you use it more than 10% of the time. Your load factor higher than 10%. Lower than 10%, then OCGT, which is the gas plants, would be more economical. Okay, so pump storage therefore permits continuous operation of our baseload plant, as I've explained before. Because baseload plants can operate more efficiently, it saves fuel, and also saving of fuel, coal-fired station is also saving the environment. Provides rapid response. If there's any sudden change in our load demand in the system, say you have a trip of a power station and suddenly you need to power up your plant, it can do that from standstill to full generation within 4 minutes. And if you were pumping and you suddenly have to stop pumping and generating again, we can do it within 7 minutes. And you can actually, by doing that, you actually double the capacity of a pump storage to the grid. Because while you're pumping, say you've got 1,000 megawatt pump storage, you consume 1,000 megawatt. If you stop pumping, immediately you regain that 1,000 megawatt, and then if you start generating, you add another 1,000 to the grid. Contribution to the network stability, it has a very large runner and very high rotating masses, so the inertia is very high, and any fluctuation on the grid can be accommodated by that high mass, rotating mass. And then there's another one, a synchronous condenser operation. During pumping and during generation, you can actually rectify the power factor on the grid by playing with your induction of your electrical motor. We also have black start capabilities of each pump storage. Should we have any blackouts, you can power up the grid again from pump storage. And as you probably know, we also use them in 2 occasions for water transfer to Swiss Water Affairs. The one that's the Drakensberg, you all know. And we also have Palmit has that facility. And we were also planning Tubatsi to have that facility. However, Tubatsi has been put on hold, probably for the next 20 years or so. Where Ingula is, the lower reservoir is in the KwaZulu-Natal province and the upper reservoir in the Free State. 4 units of 333 megawatt each, that is net power. The actual unit is 342. Rated head, we have chosen it to be 441. You can play with your rated head to decide where that is, that optimum point. That was 441. Our dams has got the capacity of storing 16 hours of full generation of the 4 units. And a cycle efficiency around about 77. That's what we estimate at this stage. But obviously, the proof of the pudding is in the eating when we start up the machines. Ingula got the lower and upper reservoir, lower on the right-hand side, upper reservoir in the higher up. Access is via what we call the main access tunnel, MAT. This is a tunnel from there going underground. It's a tunnel of 8 meter by 8.5 meter, big enough to accommodate the large transformers. And then we have various other access tunnel. There's one here to the surge chamber. And this is the first tunnel we built. It was an exploratory tunnel. And it's now we have converted it into, well, it will be converted still into the cable tunnel to get the HV cables out of the ground onto the surface. Powerhouse somewhere in the 350 meter roughly below ground surface. And then waterways, first an open canal, and then from here it's all underground. And then power lines. We have a surface yard, an HV yard on surface, as opposed to in Drakensberg that would be underground, as this was a cheaper solution. And also, we could not actually have created a link yard like Drakensberg half on top of the mountain. It would have been too much of an environmental impact. Waterways, typical cross-section. The first part is 6.6 meter in diameter, two tunnels, concrete lined. Then it changed into steel lining all the way to the powerhouse. The reason why, theoretically, you need a steel lining if the internal pressure is more than your in situ rock stresses by a certain margin. And I will come to that margin. And using that philosophy, we probably we needed a steel line around about here in the center. But however, we have quite a number of fractures in the rock, and we were quite concerned that if we would carry on here with a concrete lining, that we would leak into this, into the water into the escarpment, and that it will actually then run down the mountain. A worst case scenario. So we didn't want to take the risk and extended the steel liner. Oh yeah, and then downstream here is a single tail race of 9.4 meter in diameter. Now we did all sort of optimization. What is best, 2 tunnels, 1 tunnel, and look at the operational requirements, and came to this conclusion. And in fact, it was exactly the same results that we have in Drakensberg. Drakensberg is configured like this. We went out to tender with an inclined shaft. The contractor then asked whether this can be done. He said, okay, it's acceptable. We have that in Drakensberg. But then we would have then paid extra to that. So, well, sorry, you either give us this at the same price or not. Then he came with another solution. It was a bit cheaper for him. But that would have meant a lot of environmental impact. We had to construct an access tunnel to this point. Also, expecting this liner would have been much easier for us at an inclined than a vertical shaft, because these steel liners need to be inspected every 5 years. Anyway, these were the advantages of the contractor, that he has done that type of construction before, and he reckoned the construction time would have been shorter and more safer. Okay, we had 4. The last night was the last one. Well, was another one. Fatalities on site, but none of them was linked to these tunnels. It was all like people's getting run over on site. That was the case last night as well, unfortunately. We preferred our inclined option for these reasons, and because we never got an advantage from, a cost advantage from the contractor, we stuck to our original tender design and have an inclined tunnel. If you would design a pump storage scheme, the first thing that you look at, what size of dams do I require? What we followed, in Drakensberg, it was quite easy. It was decided we use a 28-hour dam. And together with the additional pumping we have to do with water phase, it came out to a certain volume that we required. Here was a different story. We said, okay, we already have two pump storage schemes with large storage capacities. We probably don't need this anymore. This is huge storage. So let's look at the total system cost. And by changing the various dam sizes and doing this total system cost, we actually found out what the most optimum size was. That is then the one way we did that. But we also said we want to use this pump storage at least at a 20% load factor in the week. And we always want to retain 4 hours in the upper dam for emergency conditions. So these are the 2 criteria we used, and from that we came up, it resulted into a 16-hour upper dam and lower dam. The waterways have been designed for 5 meter per second velocity and sized. At overload we accept 5.5 meters per second, steel liner 8.5. Now you can do all sort of fancy calculations using electricity price against hydraulic losses and see what is the optimum. Don't even go that route, because electricity prices change so much in future. You will end up with the wrong answer in any case. So rather use these more scientific figures. The other thing that's important is to locate your surge tanks or shaft and chamber, so that this ratio, machine starting time over water starting time, we used more than 3, we were conservatives. Some people used 2.5. And there are some formulas for that. But you can work it out from first principles, what that means. Basically, machine starting time is if I have the full pressure of water pressure against the machine, and you open the guide vanes, how long will it take to spool up the machine to the rated speed? Steel liner, there's the factor of safeties that we've used, where to use a steel liner, if the minimum in situ stresses is less than 1,2 times the maximum transient pressure. That's when a steel liner is required. And we also check it with static pressure. And the search will only happens when you start up or you stop any change of flow into your waterways. And there can be various combinations to determine what is the maximum surge. We found that for Ingula, if we are pumping and we have to stop pumping, say national control said stop pumping because I need to recover some of the energy. And then he may say 173 seconds after that, because that is the most critical time if you start generating again. And I'll show you just now why. Start generation, and then suddenly you get a trip on the total system at time 277. And that's when you get the maximum surge. So it's playing around with all sort of conditions. And the steel liner has been designed according to the European code, CECT. You are pumping, that's at time 0, still pumping. This is the level of the surge, of the water level in the surge shaft. Now you stop pumping. Immediately you stop that column of water. You stop that, but this is still carrying on. So it sucks actually water from the surge shaft, and the surge level drops. Suddenly now you put motion into the surge. So if you put motion downwards, it will go upward again. And then at that point, just when it wants to go down, national control tells you, right, start generation. Now you revert this flow downwards, and you suck all that water out of that surge. Well, not all, but most. And you create that very low point. And just when the surge is going up, you trip. And that's when you reach the maximum surge level, and then we add another 2 meters on top of that for safety factor. And then you get a pressure difference of this, and the waterways are designed for that pressure Now, the pressure at transient condition is something, I think, 733 meters, which is quite a head. That needs to be contained, and we use rock tough steel for that at 690 megapascals. Was bent on site, as you can see, quite a big bending machine. And it was actually on the limit of this bending machine, because it delivered, the steel that delivered was actually closer to 800 MPa. So to yield the steel was quite an effort. The intake, we've done a whole CFD analysis for the intake to find out what is the best configuration for the least hydraulic losses. And we found if we put, and I always call it a hydrofoil, because I didn't have another name for it. That's an extra blade in the waterway here. And that actually reduced quite substantially the intake losses. The upper dam is actually in a very sensitive environment. It's a wetland, the start of a wetland, so we had to be very cautious in designing this. You can see the wetland here. This is all wetland, and this is actually our basin. The upper dam is a rock-fill dam with a concrete face in most places. And the reason was because we didn't have enough clay on site. We only had clay for this bit here, for a clay core. Now, if you If you look at this outlet, it's a very strange shape of outlet. And there's a specific reason for that. Because it's in a wetland, we actually had to release the water evenly into the wetland as low as possible velocity, so that you don't get erosion of the wetland. We did it by selecting various shapes of outlets. You can see this one was one of the first. There's quite a variation. This is the overflow. There's quite a variation in flow. As we start to change, you could see this is practically the same velocity. And if the velocity is the same, then you get the least velocity. During construction also, the wetland is here, and here, of course. We had to divert the water into a stilling pond, and from there it was released into the wetland. We also found quite some interesting archaeological artifacts, and according to the specialists, quite a number of millions years ago, these type of creatures lived in the upper basin. This was during construction of our outlet works for the dam, upper dam still, conduit. And this is sort of almost complete. Outlet works on the right hand side, and quite a neat dam at the moment. It actually, and I'm very proud to say, it has won 3 awards. The last SICE award was also allocated to this dam. The lower dam is a roller compacted concrete dam, just a normal gravity dam. It is an arch shape, but hasn't got an arch effect. It's just because to meet the contours more or less perpendicular here. Typical section. Yeah, that was during construction. And further photos, I think, a bit further. And that was some concrete repair work to the face. And that's where it is. And the dam filled up within a few months' time. We were quite fortunate to have had a flood. And here we were commissioning one of the outlet valves. The dam has spilled again a few weeks ago. And there you can see the outlet works in the distance. Powerhouse complex. We started off with our exploratory tunnel. Then we went down in sort of, I call them spirals, but just to go down and at various levels of the powerhouse. Because we don't have a lift in the powerhouse, we wanted to do away with it. But we needed then access to various floors by trolley or by car to take out equipment. We do have a crane that goes all the way down, but you don't actually want to open big hatches just for if you want to lift the pump out, for instance. So we use those, what we call spirals. The machine hall and transformer hall. Machine, transformer, linked by the bus bar tunnels. Various adits, waterways, outlet, ventilation, typical section of the 2 caverns. You can see it's a vertical turbine, generator and runner with a ball valve, the main inlet valve, spherical valve. We modeled the underground by 3-dimensional flak analysis, just to get a feel for the stresses and to design the rock support system. Right, if you design a runner for such a big scheme, you can't buy them off the shelf. They first will do a CFD analysis and determine the runner blades, the number of runner blades, the size of the blades, and then from that they build a model out of copper. That model was about that size, It's about 400. The real size is 4.2 meters, so it's about 1 in 10 scale, roughly. And then we tested that model into a test apparatus. You can see there its model is. There's glass cover there. You can see how the water flows through the model. And from that you determine what the efficiencies are. And then we got that final version there here, that the efficiency at 85 cubic meters per second per machine at that head is 93%, which is quite a high efficiency. And at pumping it follows a similar figure. Now when you have a contract with your supplier, you set certain aims, and he then tender to supply these high efficiencies, and there's a penalty if he can't reach the efficiency after the scheme has been built. We will then get a reduction. Plotting, Ingula, specific speed graph, it plots there. There is nothing out of the ordinary, a bit higher than the Drakensberg and the Palmyre scheme. This was the manufacturing of the stay ring that was done by Turbine here in South Africa. The draft tube was done in Kenya, and the runner is done in Void, South America and Brazil. This is the spiral, also done by Turbine, because this was a few months ago. You can see this is the first draft tube, and that has now been concreted up to this level already. That's the spiral. The spiral came to site in two parts. That's been then welded on site. Then of course we had to take the power out, so we have 3 lines in pump storage of that sort of magnitude. We need to have a loop, and we need to have a redundant supply as well. So the loop gives you 2 lines, in and out, and then the third line is the independent line. And this, you won't see this but that was this winter, the upper side, and this is my story. Thank you very much.